Good evening, everyone. Thank you so much for coming. The title of my presentation is the Seismic Performance and Post-Earthquake Reconstruction of Stone Masonry Buildings in light of 2015 Nepal earthquake. This is the contents of my presentation. I will be repeating this as I go through the presentation, so I'm not going to read this here, but I will mostly focus my study on the seismic performance and reconstruction of the stone masonry typologies in Nepal. You have already seen these numbers. Basically, Nepal is one of the most seismically active countries in the world and has experienced devastating earthquakes of magnitude more than 7.5 every century. The 2015 earthquake had a main shock of 7.8 magnitude, which occurred on 25th April 2015, and was followed by two strong aftershocks within 20 days, but with epicenters at different districts, as you can see on the map. About 9,000 casualties were reported and another 22,000 were injured. The seismic sequence resulted in an economic loss of about $7 billion US, and half of which was contributed by the housing sector damage. So with respect to the damage to residential buildings, about 500,000 houses were destroyed, completely destroyed, and 250,000 houses were partially damaged. In severely hit mountainous districts, as you can see here, these are severely hit mountainous districts in the north. More than 60% of the damaged houses belong to stone in mud mortar masonry typology. So the same thing is shown in this by these red dots, which represent the damage grade 5, which is concentrated mostly on the north part of the country, where the stone in mud mortar typology was most common. This slide shows the typical recurring failure modes that the stone masonry typology experienced during the 2015 Nepal earthquake. The separation, vertical separation of cross wall, and which triggers the complete collapse, outer plane collapse. The gable damage, delamination of thick walls which lacked proper through stones to connect all voids, and there were several cases where in-plane damage was also observed. Before presenting the numerical analysis on these typologies, I want to raise some pressing issues in the ongoing post-earthquake reconstruction. The reconstruction approach followed in Nepal now is owner-driven, with partial financial assistance of about $3,000 US from the government. And the government is supposed and is providing technical assistance, mason training, and other facilitations so that people can rebuild their houses as soon as possible. After 4.5 years since the earthquake, about 58% of the beneficiaries have completed the reconstruction of their houses, so another 40% still remains to be completed. There are varied reasons for overall slower construction process, as well as there are regional variations in rural and urban settings. And the reasons are unstable government, recent transition into federal system, economic hardships, coordination issues between various stakeholders, local, national government, NGOs, and others. And there are some issues related to construction materials and availability of skilled laborers. Sorry, yeah. So first issue, and which is most important issue in the post-earthquake reconstruction, is that if you compare the top row and bottom row of houses, the top row shows the photographs of pre-earthquake houses, pre-earthquake stone masonry typology, and the post-earthquake newly built houses. You can easily see there is so much difference, and the purpose of building a house is to provide safe and sufficient space for its occupiers, rather than only to be able to withstand stronger earthquakes. That's not the only reason. So if you compare these two houses, these are mostly single-storied. New houses are mostly single-storied, while the previous pre-existing houses were almost 2 to 3 storied generally. Now, if you compare the footprint of these houses, the footprint are almost comparable or even smaller in these houses. So making 1 to 2 rooms available only. And these houses further lack the typical layouts of a house, for example, living room, kitchen, bathroom, bedrooms, and so on. You cannot see any provisions of those. And most of the rural communities are farmers. They have farming, so crops, cattle sheds, they need all these things, but those provisions are not seen in these houses. So when I was in the field doing survey and interviewing people, there are several reasons for constructing these small houses emerged. And the most common reason is the economic hardship of poor people in the rural communities. They couldn't afford more than that. So if you compare the construction cost of different typologies, this is the construction cost of newly built typologies. So the construction cost of stone masonry, this also includes mud mortar and cement mortar both, is about $5,000 US, and the government provides financial assistance of $3,000. So they need to add almost half to even build a single-story 2-room house. Another reason is the lack of adequate technical information and assistance. So, for example, there were messages spread in the communities that smaller houses are more earthquake resistant, which is true. But that's not the sole purpose of building a house. And for constructing larger and multi-storied buildings, there was not enough technical assistance from the field engineers because they themselves lacked appropriate training from the government. Another reason is people built it in the immediate aftermath of the earthquake just as a temporary solution, and they are saving money to build larger multi-storied houses in the future. This is funny. There are several cases, there are reports that monetary interest has motivated people to build small houses and further compromising on the quality of construction so that they can build with money below $3,000 US so that they can make profit out of that financial assistance from the government. Another issue is the quality, workmanship, or non-compliance issues. So the main issue in the workmanship can be observed in the seismic bands, as you can see in these photos. So the most probable reason for this is the local masons are not well trained for using modern materials. They are familiar with traditional construction, such as using timber and stone. So the non-compliance issues, which is the non-compliance with respect to the Nepal building code, is more frequent in multi-storied and large span houses. For example, this house, the bands are not placed appropriately. This is not enough. And so this makes it non-compliant. And after the earthquake, after the heavy damage sustained by the stone in mud mortar typology in the rural area, people are believing that modern construction materials make the houses seismic resistant, kind of automatically. But that's not true. It all depends on how you put all materials and work together. As an example, so the engineering-based minimal improvements of the local crafts, which have been practiced since centuries, can result in sustainable and seismic-resistant structures. For example, you see this house, it is an 80-year-old house that is still standing there, and that has stood 3 major earthquakes in the past. This includes seismic enhancement features of timber elements, for example, these vertical posts, compression struts supporting the roof and floors, and the walls include timber bands, 2 per story, so making it seismic resistant. Now, I'm focusing on the construction characteristics of stone masonry in mud mortar buildings. Before that, I will zoom into the wall level to show how these walls are constructed and what the materials are. The stone units used are from various nearby sources, for example, from river, from the quarry site, and so on. And the same is mortar. They will find anything available around and make the mortar out of that. So this means that the quality is not controlled, and the stone varies largely on its shape and size both. These stone masonry walls are typically thick, 400 to 600 millimeter, with 2 to 3 voids of usually uncoursed random rubble stone. So throw stones are provided in many cases, which are not adequately provided though, although the National Seismic Code puts these guidelines. In some buildings, these stones are flat. If you see the first figure, the stones are flat so that horizontal courses can be seen, while in the fourth figure, if you see, stone shapes are more irregular, so you cannot see distinct horizontal courses built. Due to such variations in both material quality, shape, size, and in the workmanship, all these will result in large uncertainty in the mechanical properties and hence the lateral seismic resistance of these constructions. Now, this slide presents the construction characteristics of pre-earthquake typology, which is multi-storied, 2 to 3 storied. And besides the load-bearing system, it has a central timber frame system, which also takes some of the lateral load. And the floor and roof structures are made of timber elements, and the roof particularly is held together by compression struts locked into timber keys, so binding all the walls together to improve the global behavior. While in the post-earthquake typology, newly built typology, this typology follows the seismic design code. These buildings, the pre-earthquake buildings, do not follow seismic design codes traditionally built, while these buildings, newly built buildings, follow the seismic design code, and it includes seismic bands at sea level, lintel level, roof level, as you can see in the recently constructed buildings. And the roof is very light structure with light covering. Now I will present the results of the numerical modeling and analysis of these two typologies. So before that, the modeling tool we have adopted is the applied element method, in which we have followed simplified micromodeling technique. So basically, stones are considered as rigid elements, and all the deformability of the material and nonlinearity is concentrated at this interface represented by these springs, which can fail. After the failure of springs, the elements can come in contact and friction can occur. So this is the strategy we have followed for modeling rubble stone masonry so that we can get irregular shaped stones. That's the software we have used, extreme loading for structures. Now, before using the tool to apply at the building level, we have reproduced several, I'm showing only 2 here, but several experimental test results using the numerical analysis to validate and calibrate our numerical modeling tool. And as you can see, both the crack pattern as well as the load deformation behavior from the numerical analysis match well with the experimental results. So that gives us more reliability on our modeling and results. So these are the numerical models of the pre-earthquake and post-earthquake typology. So for the pre-earthquake typology, all the timber elements as they impart a rigid diaphragm action to the building are explicitly modeled, as you can see, while the roof is neglected in the post-earthquake typology because of its being light. As the material properties are key inputs for the numerical modeling, we have used the material properties obtained from recent tests on Nepalese stone in mud mortar masonry conducted by Bill Change. If you see these numbers, these are far lower than what you see for normal masonry. Further, to consider the uncertainty in the material quality, we have considered two different material quality. Poor quality by reducing this further down by 50%, and good quality by increasing these average values by 50%, so that we can see the effect of uncertainty in the material quality. This slide shows the analysis results for the pre-earthquake typology. This is the capacity curve for two directions, the longitudinal and transverse. As you can see in the both directions, the capacity is too low, 0.12 G only. And that's the maximum, and the weakest is the transverse direction, shorter direction. In terms of collapse mechanism, in both direction loading, you can see the collapse of shorter wall occurs, which is most common in observed damage pattern as well. In the longitudinal direction loading, because of the presence of opening and torsional effect, corner failure occurs here, and some shear damage and delamination occurs here. While in the transverse direction loading, this wall has an opening here, so the shear damage starts from the corners of the opening, thus triggering the collapse of the wall. In both cases, if you see the excessive out-of-plane displacement is controlled, that means the timber floor and roof structure provides sufficient diaphragm action for both direction loading. Similarly, for the post-earthquake typology, because these are single-storied, so obviously better seismic performance, the capacity curves in both directions are very similar, so it has equal strength in both directions, reaching as high as 0.6 G. And the damage pattern here is a bit different. It's shear sliding damage pattern which originates, which is at the wall band interface, and the shear diagonal shear failure of these walls is controlled because of the presence of the seismic bands. In terms of material, the effect due to material quality, if you see here as well, the effect of material quality, and here as well, so it can cause a lot of variation in both ductility and strength. So the material quality should be given importance in the construction. Now I will present the seismic performance assessment results for both typologies. So as per the Nepal building code, the pre-earthquake typology performs far, far beyond the ultimate limit state of these buildings. This is using N2 method. So, and while the new typologies perform within the immediate occupancy, the serviceability limit. But if you consider the material quality variations here, the capacity curve could be somewhere here as well. If you compromise material quality, so the serviceability limit could be challenged. In terms of fragility functions, because there are no enough ground motions from Nepal, we have used FEMA P695 suite of ground motions to generate these fragility curves. To summarize, for the pre-earthquake typology, the median PGA capacity for the serviceability limit state is 0.05 G, while for the ultimate limit state is 0.3 G only. These numbers are considering good quality materials. While for the post-earthquake typology, the median PGA capacity for serviceability is 0.17 G, and for ultimate it's 0.8 G, even with considering poor material quality. So that shows the difference in seismic performance of these two buildings, but we should also note that the post-earthquake typologies are mostly single-story. That's why better seismic performance. Now we have also developed seismic fragility curves, vulnerability curves, using those fragility curves presented before and the damage to loss function given by Hazes. If you see the dispersion due to the material quality in the pre-earthquake and both post-earthquake typology, it's plus minus 50%. So it can cause a lot, the material quality can cause a lot of dispersion in the PGA capacity. If you compare both together, for simplicity, I have just compared the average of both. The pre-earthquake has a PGA capacity of 0.11 G for 50% mean damage ratio, while the post-earthquake typology has a PGA capacity of 1 G for the same level of damage loss. So, and if you compare the numbers from the 2015 Nepal earthquake, the USGS 2015, that estimated a PGA range of 0.3 to 0.8 G in the most affected district. So you can compare these numbers against this number, and the heavy damage was inevitable. These are some of the conclusions. This is just the summary of what I presented, so I'm not going to read all this, but as a future work, since the retrofitting of pre-earthquake typology is currently ongoing on both damaged and undamaged buildings, so we will focus our future work on comparative comparison of the improvement after the retrofitting in these typologies. Thank you very much for your kind attention. Here is the project report. You can download it from here. Thank you.